Japan is the 10th most populous country in the world, with an estimated population of over 130 million people. And a large part of this population lives in cities. Every day, thousands of people travel to various places, including schools, workplaces, leisure areas, and others. Moving this huge mass of people by air would mean that 3 jumbo jets would have to take off every 5 minutes, which would not be cheap at all and would drastically increase pollution levels. And they do. Roads aren't a good idea either, since they're already very congested. The solution chosen by the Japanese was the train. Trains are means of transportation capable of carrying a large number of people and cargo, and they've been used for over 100 years and are the 3rd safest means of transportation in the world, only behind airplanes and elevators, which are considered the safest means of transportation. Even with the introduction of modern trains, which are much more advanced, sophisticated, and much faster, they still couldn't meet the huge transportation demand in Japan. Japanese engineers then wanted to redesign the conventional train, making it much faster and capable of reaching 320 km/h, so that key routes like the Tokaido Shinkansen and Sanyo Shinkansen could be traveled several times a day and in much less time. That's how bullet trains were conceived. But how do you turn a conventional train into a high-speed train? Conventional locomotives, which at best reach 70 km/h, wouldn't withstand the stresses that a trip at 300 km/h puts on the structure. Therefore, for high-speed trains to become a reality, it was necessary to completely redesign them. But redesigning them was not enough. It was also necessary to reinvent the wheel and find some way to keep them on the tracks at those speeds. And it all starts with the shape of the wheels. A conventional locomotive wheel may seem like a simple item, but it hides some critical features that, among other things, allow the train to go around curves and, most importantly, prevent derailment. Although at first the wheels may appear to be cylindrical, when we look closer, we notice that they have a semi-conical shape. The outer edge has a smaller diameter compared to the inner edge, thus forming an angle that ends with a protrusion called a flange. This protrusion, which sits much lower than the rails, is very important, and it is what prevents the wheels from slipping off the rails. This design, where the inner edge is larger than the outer edge, has the main function of allowing the train to make turns. But how? Imagine that the train needs to make a left turn. To make a left turn, the wheels on the right side have to travel a greater distance than the wheels on the left side. This means that the wheels on the right side for a short period of time have to spin at a higher speed than the wheels on the left side, because the distance they travel is greater. That's exactly what happens in an Olympic race. The athlete running on the track with the smaller circumference must start much farther back compared to the athlete running on the track with the larger circumference. That's because the distance covered by the athlete on the track with the smaller circumference is much less compared to the distance covered by the athlete on the track with the larger circumference. However, train wheels do not rotate separately or at different speeds. That's because they are connected by the same axle, which only allows them to rotate together. That's where the semi-conical shape comes in. When making turns, the wheels on the outside of the curve have a slightly larger diameter compared to the wheels on the inside of the curve, slightly shifting the center of gravity toward the direction of the turn. In other words, when the train turns, it is momentarily running on wheels that are effectively 2 different sizes. The larger wheel compared to the other allows the turn to be made, even though both are spinning at the same speed. But when the train is not turning, that wheel shape creates a dangerous oscillation phenomenon known as hunting oscillation, which is simply the wheels swaying from side to side continuously, which tends to intensify as the speed increases, which would be potentially catastrophic for a train moving at more than 300 km/h. That's why, to achieve higher speeds, trains stop using wheels to reduce noise, reduce friction, and to be safer. And that's why China's magnetic levitation trains, or Maglevs, don't use wheels at high speeds. They levitate at a small distance that ranges from 1 to 10 centimeters above the tracks. With the entire weight of the train supported by an invisible magnetic cushion generated by the repelling force of powerful magnets located both on the train and on the tracks. But because the train needs to levitate in order to move, this means that the entire railway line has to be electrified, which poses a great danger. But according to its designers, only the area where the train is near or passing through will be electrified. Add to that the fact that it's necessary to build thousands and thousands of kilometers of new special railway lines dedicated only to these trains, and the Maglev project ends up being very expensive. That's why they are still not a reality. Returning to Japanese bullet trains. To eliminate hunting oscillation, the engineers modified the shape of the wheels, almost completely removing that semi-conical shape, making the wheels straighter. The wheels still have a slight angle that helps with turns, but another system was created to help even more with turns, which is a tilting mechanism based on air suspension and high-precision position data, which is basically a digitally controlled system, extremely precise, that predicts and anticipates the turns and tilts each of the 16 cars precisely at the exact moment. This system tilts the train up to 1 degree of lateral inclination, keeping the lateral acceleration felt by passengers below 0.9 meters per second squared. With the train going through a curve with a radius of 2,000 to 2,500 meters, moving at 270 km/h, that was one of the required specifications. By the way, the N700 series of Shinkansen trains was the first to adopt such a precise tilting system as this. And the train would not be certified, nor would it be safe and comfortable enough to operate if a system like this had not been created. Several computers, solenoid valves, sensors, pneumatic circuits, electrical circuits, and microcontrollers work together, adjusting the height and tilt of the train thousands of times per second. And all of this is done in milliseconds, with all the computers and pneumatic circuits being fault tolerant. You can imagine that the rails of a railway line are not perfect. There are sections where the rails are closer together and others where the rails are farther apart. And this misalignment gets worse with the thermal expansion of the metals that make up the railway line. And this would cause a lot of shaking and 100 other problems for a train that moves at more than 300 kilometers per hour. So what do? The solution is to install a set of springs, just like in cars, to absorb the impacts and imperfections of the railway track. Not just vertical impacts, but also horizontal imperfections. This way, these springs allow the wheels to move apart from each other horizontally, absorbing the imperfections of the tracks throughout the entire route. With the wheel problem solved, the next challenge is propulsion. Bullet trains are essentially electric vehicles, which means they move thanks to a set of electric motors, 56 to be precise, each rated at 305 kilowatts, distributed across 16 cars. But unlike electric cars, which store energy in batteries to later distribute it to the electric motors, bullet trains do not use batteries. The electrical energy received is sent directly to the electric motors, which in turn propel the train. But where does this energy come from? Well, from an electrical grid right above the train, which simply carries from 25,000 volts at 60 hertz in alternating current. And for this energy to reach the train, a device called a pantograph is responsible for carrying out this task and for maintaining constant contact with the electrical grid right above. And this is very important because if this contact is lost, two things happen. The train loses power and consequently stops. And the second is that electric arcs are formed with temperatures above 1,200 degrees Celsius, which damage the overhead power lines and also damage the pantograph due to overheating. The pantograph must then maintain constant contact with the overhead power lines by applying a force that must be within a well-defined range from 70 to 120 newtons. If the force is lower, the pantograph loses contact and electric arcs occur. And if the force is higher, the resulting friction will wear out the overhead lines prematurely. That's why pantographs are designed to have variable vertical movements, so that even in sections where the overhead wires are looser or tighter, contact is never lost. But it doesn't always work. In general, the NN700 is an electric train with its structure made of aluminum, with each car being 25 meters long, except for the front and rear cars, which are just over 27 meters. It has a maximum speed of 360 kilometers per hour, but it is limited to 300 kilometers per hour because of the condition of the tracks and also due to the existence of tighter curves that could cause the train to derail. It has a total weight of 715 tons in the 16-car configuration, 56 motors of 409 horsepower each, which together deliver 22,904 horsepower. It accelerates from 0 to 300 kilometers per hour in 180 seconds. This entire system requires 25,000 volts of alternating current at 60 hertz. And this longer nose at the front isn't for style, nor is it a bumper for possible collisions, and it certainly doesn't hide any kind of bullet train machinery. This nose is essential and serves two very important purposes. The first is that it provides much better, more efficient aerodynamics, especially at high speeds. In other words, the air flows much better and with very little drag. And second, it reduces the piston effect, also known as tunnel boom, which is basically the noise that happens when a high-speed train enters a tunnel at high speed. The air around the train displaced at high speed is forced into the tunnel, creating powerful shock waves. Besides noise and vibrations, additional forces can damage the tunnel and nearby structures. But even with so much innovation, Japanese bullet trains still face serious danger simply because they operate in Japan. An unpredictable, devastating enemy that you can't see until you're hit by it. Earthquakes. On average, Japan is hit by an earthquake every 5 minutes, most of them ranging from 1 to 3 in magnitude. This scenario doesn't seem very good for the thousands of people who are constantly traveling at almost 300 km/h on bullet trains. And from experiences in past events, engineers already knew that in major earthquakes, the tracks are completely destroyed, causing several trains to derail, especially those moving at high speeds. The engineers then needed to develop some way to detect earthquakes in advance. In the study of earthquakes, it was already known that in a seismic event, there are P waves or primary waves, which are the first very small, not very destructive waves and are difficult to detect. And they travel at high speeds much faster than the later waves called S waves or secondary waves, which are relatively slower, high energy, and easily detectable. However, once they arrive, little can be done. Knowing this, the designers of the NN700 focused their efforts on creating seismometers and other equipment that were really sensitive and capable of detecting the P waves. And this system that was created, which works together with the local meteorological agency, is called Terra-S, which is a set of seismometers and other equipment spread along the coast and at other points in Japan. This system calculates the magnitude and epicenter of the earthquake in just 2 seconds. And as soon as the system detects that the tremor is of a magnitude that poses a risk to the trains, it sends a signal and the power is cut, stopping any train that is in motion. The communication system and the emergency brake system installed on the bullet trains lead to a complete stop in a short period of time. And since earthquakes are very effective at what they do, it would be pointless to bring the bullet train to a quick and safe stop if the tunnel or viaduct where the train is happens to collapse. The other aspect of the system was to reinforce the critical structures that the bullet train passes through, such as bridges, tunnels, viaduct pillars, and even adding locks to the rails so that the wheels don't come off, even during a major earthquake. Installing metal structures on viaduct pillars to reduce excessive swaying, plus other measures.